January 5, 1943. The waters off Guadalcanal. A single Japanese dive bomber screams down toward the light cruiser USS Helena, and the gun crews, manning her 5-inch batteries, fire a weapon so secret that most of the men pulling the triggers do not even know what makes it different from any other shell they have ever loaded. The bomber does not survive the second round. It disintegrates in mid-air, torn apart by a shell that detonated not on impact, not on a timer set by a fallible human gunner, but at the precise moment its own onboard electronics sensed the aircraft passing close enough to guarantee a kill. Aboard Helena, few sailors fully grasp what has just happened. They know only that a single shell, fired almost casually amid the chaos of an air raid, found its mark with an efficiency that defies everything they have learned about naval gunnery. Captain Charles Cecil, commanding Helena that day, understands considerably more than his crew, having been briefed in advance on the special ammunition loaded into a portion of his ship's 5-inch magazine, sworn to a level of secrecy so strict that even his own gunnery officers are told only that the new shells perform differently, without being given a full technical explanation of exactly how or why. Cecil's orders, transmitted through a communications channel reserved for the small number of officers cleared to know the fuse's true purpose, instruct him to fire the special ammunition only when circumstances make recovery by the enemy essentially impossible, a constraint that will govern the weapon's use across the fleet for the better part of 2 years to come. What they have just witnessed is the first combat use of the VT proximity fuse, a device so closely guarded by American military secrecy that its existence will not be publicly acknowledged until years after the war ends, and a device that, by the time Imperial Japan finally understands what has been a raid against its aircraft, will have already helped reshape the entire air war over the Pacific. To understand why this small, unassuming piece of hardware matters so profoundly, you have to understand the problem the United States Navy has been struggling to solve since the earliest carrier battles of the Pacific War. Anti-aircraft gunnery in 1942 relies overwhelmingly on time-fused shells, ammunition engineered to explode after a set number of seconds, calculated by gunners attempting to predict where a fast-moving aircraft will be at the precise instant the shell arrives. It is an extraordinarily difficult calculation, dependent on accurate range finding, correct timing, and no small amount of luck, and the results, across the early years of the Pacific War, are sobering. Naval gunners routinely expend enormous quantities of ammunition for every enemy aircraft actually destroyed, some studies from the period suggesting it takes on average many thousands of rounds of medium anti-aircraft fire to bring down a single plane. Carrier battles at Coral Sea and Midway in the spring of 1942, followed by the brutal, sustained air campaigns around Guadalcanal later that year, exposed this weakness repeatedly, American warships absorbing bomb and torpedo hits from attackers that anti-aircraft crews had fired upon extensively, but failed to destroy in time, the shells detonating too early, too late, or too far from their intended targets to inflict meaningful damage. Fleet commanders and their gunnery officers grow increasingly frustrated, watching engagement after engagement, in which ships expend the bulk of their ready ammunition without achieving a proportional number of kills, a mounting body of evidence that conventional time-fused ammunition, however well manufactured and however skillfully aimed, simply cannot keep pace with the speed and maneuverability of modern carrier-based aircraft. Against the increasingly aggressive Japanese naval air arm, flying skilled, battle-hardened pilots in fast, maneuverable aircraft, this inefficiency represents a mortal danger to the entire American fleet. The men working to solve this problem operate under a code name that reveals nothing about their actual purpose. Section T, a division of the National Defense Research Committee established under the umbrella of the Office of Scientific Research and Development, working in close coordination with the Applied Physics Laboratory established specifically for this purpose at Johns Hopkins University. Physicist Merle Tuve leads the effort, tasked with achieving something that sounds on its face almost impossible in the technology of the early 1940s. Cramming a miniature radio transmitter and receiver, a vacuum tube amplifier, a battery, and a firing mechanism into the nose of an artillery shell small enough to fire from a standard naval gun. All of it engineered to survive an acceleration of over 20,000 times the force of gravity at the moment of firing without breaking a single vital component. Tuve's team, drawing on pre-war research into radio proximity switches, originally explored for entirely different, peacetime purposes, faces engineering obstacles that would have seemed insurmountable only a few years earlier. Vacuum tubes of the period are notoriously fragile, designed for use in stationary radios sitting on a shelf, not for surviving the violent shock of being hurled from the barrel of a naval gun at velocities exceeding 2,000 feet per second. The team tests hundreds of prototype designs, many of them failing outright during initial firing trials, components shattering or circuits shorting under the extreme forces involved, each failure feeding back into a rapid, iterative redesign process that gradually narrows in on a configuration robust enough to survive intact. Engineers redesign the internal components from the ground up, developing shock-resistant tubes, specialized batteries that activate only at the moment of firing through the force of the shell's own spin and acceleration, and miniaturized circuitry robust enough to survive conditions that would destroy virtually any other electronic device of the era. The finished design, once perfected, represents a genuine marvel of wartime engineering. A complete radio transmitter, receiver, amplifier, power source, and detonation mechanism, all packed into a space smaller than a soup can, manufactured to tolerances precise enough for mass production, yet reliable enough to function correctly after surviving forces that would crush ordinary consumer electronics of the period into scrap. The device, officially designated the VT fuse, for variable time, a deliberately misleading name, chosen to disguise its true function from anyone who might overhear it discussed, works by emitting a continuous radio signal that reflects off any nearby object, including an approaching aircraft, and detonates the shell automatically the instant that reflected signal grows strong enough to indicate the target is within lethal range. The security surrounding this technology borders on obsessive, and for good reason. Naval commanders and even senior officers within the Bureau of Ordnance understand immediately that if a single unexploded proximity-fused shell falls into enemy hands, the fundamental design of the device could be reverse-engineered, handed to Axis scientists, and turned back against Allied aircraft and ground forces with devastating effect. Officers cleared to know the fuse's true purpose are briefed on strict protocols governing its use, and ships carrying the ammunition are instructed to fire it only over open ocean, where the risk of a dud shell washing ashore or being recovered by a Japanese patrol is effectively eliminated. For much of 1943, the fuse's use is restricted almost entirely to shipboard anti-aircraft fire over open water, where any dud shell will sink to the ocean floor, rather than being recovered by an enemy soldier or scientist. It is a restriction that will hold, with only the rarest exceptions, for the better part of 2 years, even as commanders in other theaters plead for access to a weapon they have heard whispered about, but are not permitted to use. Army ground commanders in Europe, aware of rumors surrounding a new type of shell that could dramatically improve anti-aircraft and artillery effectiveness, repeatedly request permission to deploy it against German forces, only to be told that the security risk of capture on a land battlefield, where a dud round could easily be picked up and examined by enemy technicians, remains unacceptably high until circumstances in the war shift decisively enough to change that calculation. By 1943, Fleet Admiral Chester Nimitz, commanding the entire Pacific Fleet from his headquarters at Pearl Harbor, has begun receiving reports of the fuse's extraordinary effectiveness, reports that circulate among his senior staff with a mixture of professional excitement and disciplined restraint, aware that discussing the weapon too openly, even among trusted officers, risks the very security breach that could neutralize its advantage forever. Nimitz himself, known throughout his command for a measured, understated leadership style that rarely betrays enthusiasm openly, reportedly reviews early combat reports on the fuse's performance with unusual attention, aware that a technology capable of multiplying the effectiveness of every anti-aircraft gun in the fleet represents exactly the kind of quiet, decisive advantage that could shift the balance of an increasingly brutal air war without requiring any additional ships, guns, or men. What Nimitz's staff comes to understand about this device, and what they are extraordinarily careful never to say aloud where the wrong ears might be listening, will shape naval combat across two of the most consequential air battles of the entire Pacific War. But in January 1943, none of that lies yet in view. All that exists is a single cruiser off Guadalcanal, a single dive bomber torn from the sky, and a question that will not be answered for another 18 months. How much of the coming war in the Pacific will be decided by a piece of equipment the Japanese Navy does not even know exists? Through the middle months of 1943, the VT fuse spreads gradually across the fleet, installed aboard an increasing number of American warships, even as its true nature remains rigorously compartmentalized, known in full only to a small circle of officers and technicians, cleared to understand exactly what makes the ammunition different from ordinary time-fuzzed shells. Production ramps up dramatically under wartime industrial mobilization, American manufacturers eventually producing proximity fuses by the millions, a scale of output that would have been unimaginable when Tuvey's team first struggled to fit working radio components into a shell small enough to survive being fired from a naval gun. Companies previously manufacturing consumer radios and electronics retool their production lines almost entirely for fuse manufacturing, a conversion of civilian industrial capacity to military production that mirrors, on a smaller and far more secretive scale, the broader transformation of the American economy for total war. Workers on these production lines are themselves rarely told the true purpose of the tiny components passing through their hands each day. A compartmentalization of knowledge that extends from the officers commanding warships in the Pacific all the way back to the factory floors of the American Midwest. Each link in the chain understanding only the narrow piece of the process assigned to them and nothing more. Bureau of Ordnance officers track effectiveness data obsessively, comparing kill rates between VT-fuzzed and conventional time-fused ammunition across every engagement where the new shells see action, building a body of statistical evidence that, while never publicly discussed during the war itself, convinces an increasing number of senior commanders that they are sitting on a genuinely transformative weapon. The moment that data becomes undeniable arrives on June 19, 1944. Japan has committed the bulk of its remaining carrier aviation to a desperate effort to break the American advance into the Mariana Islands, launching wave after wave of aircraft against Vice Admiral Mark Mitscher's Task Force 58, a fleet built around 15 fast carriers and screened by a formidable array of battleships, cruisers, and destroyers, nearly all of them now equipped with proximity-fused anti-aircraft ammunition. Vice Admiral Jisaburo Ozawa, commanding the Japanese mobile fleet, has staked the remaining strength of Japan's carrier air arm on this single, decisive engagement, believing that superior aircraft range and the advantage of striking first can offset the numerical and material disadvantages his forces face against the accumulated industrial might of the American Pacific Fleet. It is a gamble built on assumptions about American anti-aircraft effectiveness that no longer hold true. Assumptions rooted in the gunnery statistics of 1942 and early 1943, rather than the transformed reality the fleet's ammunition magazines now contain. What follows becomes known, almost immediately among the American sailors who witness it, as the Mariana's turkey shoot, a nickname that captures both the scale of the slaughter and the almost disbelieving tone with which American gunners describe an air battle unlike anything the Pacific War has yet produced. Japanese pilots, many of them poorly trained replacements rushed into combat after the crippling losses of 1942 and 1943, pressed their attacks into a wall of anti-aircraft fire that, thanks to the proximity fuse, no longer depends on the split-second timing accuracy that has limited American gunnery effectiveness for the previous 2 years. American fighter pilots flying the new Grumman F-6F Hellcat, itself a substantial improvement over earlier carrier aircraft, intercept many of the incoming Japanese formations before they even reach the fleet, but a significant number of attackers press through the fighter screen regardless, only to encounter an anti-aircraft barrage that behaves in ways Japanese pilots, trained and briefed based on the fleet's earlier performance, have no way of anticipating. The results are catastrophic for Japan. Of the roughly 373 carrier aircraft Japan launches against the American fleet that day, Japanese naval aviation loses an estimated 240 or more planes, the overwhelming majority shot down by a combination of American fighter aircraft and the newly lethal anti-aircraft fire pouring up from the fleet below. American submarines, operating independently of the surface battle, sink 2 of Ozawa's carriers that same day, compounding the catastrophe for a Japanese fleet that entered the engagement already at a severe material disadvantage. The scale of the defeat leaves Japan's carrier air arm effectively shattered as an offensive force for the remainder of the war. The pilots and aircraft lost in a single afternoon, representing a training and production investment that Japan's strained wartime economy has no realistic hope of replacing in kind, a loss that will echo through every subsequent naval engagement of the Pacific War, including the desperate, sacrificial kamikaze tactics that follow in the campaign's final year. Born in no small part from the simple fact that Japan no longer possesses enough trained pilots to fight the kind of conventional carrier battle the Mariana's turkey shoot had just demonstrated it could no longer win. Gunners aboard American warships describe watching Japanese aircraft explode in mid-air at ranges and under conditions that, only a year earlier, would have produced a clean miss more often than not, the shells detonating automatically the instant the proximity fuse senses a plane passing within lethal range, rather than relying on a gunner's estimate of when to set a timer. Some accounts from the battle describe entire formations of attacking aircraft being decimated before they can even begin their bombing or torpedo runs. American ships putting up a curtain of exploding shells so dense and so precisely triggered that Japanese pilots, already outmatched in aircraft quality and pilot training, face what amounts to an unbreakable wall of fire. Survivors among the attacking Japanese squadrons, on the rare occasions they return to report what they encountered, describe an anti-aircraft barrage unlike anything they had been briefed to expect, shells detonating with an accuracy that seemed to defy the normal laws of probability governing conventional time-fused fire, though none of the pilots reporting these observations possessed the technical knowledge to explain precisely why American gunnery had so suddenly, so drastically improved. For Nimitz's staff, monitoring reports from the battle as they arrive at Pearl Harbor, the scale of the one-sided victory confirms everything the effectiveness statistics had been suggesting for months. Vice Admiral Charles McMorris, Nimitz's chief of staff, and other senior officers, cleared to discuss the fuse's true contribution, reportedly circulate internal assessments, crediting the weapon directly for a substantial share of the day's extraordinary kill ratio. Assessments that never leave the tightly controlled circle of officers, authorized to know the fuse's real nature, even as public accounts of the battle attribute the victory more broadly to American pilot skill and superior aircraft. Privately, among the small circle of officers cleared to discuss the fuse's true role, credit for the lopsided kill ratio increasingly centers not just on the skill of American pilots, though that skill is real and considerable, but on a piece of ordnance most of the men firing it barely understand, an invisible advantage humming inside every shell fired from the fleet's anti-aircraft batteries. Yet, even amid this triumph, a genuine vulnerability remains unresolved, one that will define the next, far more dangerous phase of the Pacific War. The proximity fuse is devastatingly effective against conventional attack profiles, aircraft approaching to drop bombs or launch torpedoes, and then attempting to escape. It has never yet been tested against an enemy willing to fly the aircraft itself directly into its target, absorbing any near miss, and continuing forward regardless of damage that would send a conventional attacker peeling away in retreat. No amount of statistical success against orthodox attack patterns can fully predict how the technology will perform against a threat built around the deliberate rejection of self-preservation, a tactical philosophy no engineer designing the fuse in the calmer years before the war had any reason to anticipate. That test is coming, and when it arrives, off the island of Okinawa in the spring of 1945, it will push the proximity fuse and the entire American anti-aircraft defense system built around it to the absolute limit of what the technology can achieve. The kamikaze campaign that erupts around Okinawa beginning in April 1945 represents an entirely new category of threat, one that no amount of statistical modeling from the Mariana's turkey shoot fully prepares American commanders to face. Japanese pilots, many of them barely trained volunteers flying obsolete aircraft stripped down and loaded with explosives, deliberately crash their planes into American ships, a tactic that renders the previous calculus of anti-aircraft effectiveness partially obsolete. Shooting down an attacking aircraft moments too late, after it has already begun its final dive, may no longer prevent the ship below from being struck by burning wreckage carrying hundreds of pounds of explosives. Vice Admiral Matome Ugaki, overseeing much of the kamikaze effort from Japanese airfields on Kyushu, understands that his pilots cannot match American forces in conventional aerial combat, and instead directs a strategy built entirely around the psychological and material shock of mass suicide attacks, gambling that sheer volume and desperation can inflict damage that skill and technology alone cannot prevent. Over the following weeks, in a sustained campaign that comes to be known as Operation Tengo's Aftermath and the broader Kikusui, or Floating Chrysanthemum, mass attacks, Japan launches an estimated 1,500 or more kamikaze sorties against the American fleet supporting the Okinawa invasion, the most concentrated and sustained suicide air campaign of the entire war. Even with the proximity fuse arrayed against them, American losses at Okinawa are severe. Destroyers and destroyer escorts assigned to picket duty, stationed far from the main fleet specifically to provide early radar warning of incoming attacks, absorb a disproportionate share of the punishment. Ships like USS Laffey enduring an onslaught of more than 20 separate kamikaze and bomb attacks in a single engagement on April 16, 1945, and somehow surviving despite catastrophic damage and dozens of her crew killed or wounded. Laffey's crew, fighting fires and manning guns even as their ship takes hit after hit, credit the ship's anti-aircraft batteries, firing proximity-fused ammunition throughout the engagement, with breaking up or destroying enough of the incoming attackers to prevent what otherwise seemed, in the middle of the battle, like certain destruction, a single destroyer facing down a sustained assault that would, under the anti-aircraft effectiveness of 1942 or early 1943, have almost certainly ended in. Across the entire Okinawa campaign, the U.S. Navy loses 36 ships sunk and suffers damage to more than 368 others, along with nearly 5,000 sailors killed, the heaviest naval losses the United States suffers in any single campaign of the entire Second World War. For a brief, harrowing period in the spring of 1945, it appears possible that the sheer volume and desperation of the kamikaze assault might overwhelm even the most sophisticated anti-aircraft defenses the American fleet can bring to bear, a genuine crisis of naval air defense that tests every technological and tactical innovation developed over the previous 3 years of war. Yet analysis conducted both during and after the campaign reveals a critical, if grim, statistic. The proximity fuse, even against an enemy willing to fly through anti-aircraft fire rather than turn away from it, dramatically increases the probability that an incoming kamikaze will be destroyed before reaching its target, or damaged badly enough that its final impact, if it manages to strike a ship at all, causes substantially less destruction than an aircraft hit dead center by a fully effective burst. Post-war operational analysis, drawing on detailed records of individual kamikaze engagements throughout the Okinawa campaign, finds that ships equipped with the most modern proximity-fused anti-aircraft batteries and effective fire control systems consistently achieve higher interception rates than vessels relying more heavily on older equipment, a pattern consistent enough that naval planners cite it directly in post-war recommendations for future shipboard defense doctrine. Naval gunnery officers begin adjusting tactics specifically to exploit the fuse's strengths against this new threat, concentrating fire to create dense curtains of proximity-triggered explosions in the final seconds of a kamikaze's approach, when even a near miss that would have been useless against a conventional bomber can be enough to knock a suicide pilot off his aim point or destroy the aircraft's structural integrity before impact. Without this capability, Naval historians and gunnery officers alike come to believe in the years following the war, American losses at Okinawa would almost certainly have been dramatically higher, potentially threatening the entire logistical and naval support structure sustaining the invasion of the island itself. When the war finally ends in August 1945, the proximity fuse emerges from wartime secrecy as one of the most consequential technological developments of the entire conflict, ranked by many of the officers and scientists who worked closely with it alongside radar and the atomic bomb as among the handful of innovations that most directly shaped the outcome of the Second World War. The National Defense Research Committee's own post-war assessment of wartime scientific contributions places the fuse among the very small number of technologies deemed to have altered the outcome of specific campaigns rather than merely improved existing capabilities at the margins. A distinction the committee reserves for only its most consequential wartime projects. Fleet Admiral Ernest King, Chief of Naval Operations throughout the war, along with Nimitz himself, privately credits the device in post-war assessments shared among naval planners and eventually reflected in official Navy histories, with dramatically reducing American casualties from Japanese air attack across the final 2 years of the Pacific War, a judgment echoed by James Forrestal, Secretary of the Navy, who reportedly describes the fuse as one of the 3 or 4 developments that most changed the course of the naval war. Statistical analyses conducted after the war, comparing the destructive efficiency of proximity-fused versus conventional time-fused anti-aircraft ammunition across the full span of Pacific naval engagements, generally find that VT-fused shells prove several times more effective per round fired at destroying enemy aircraft, a multiplication of anti-aircraft firepower achieved not through more guns or more ammunition, but through a fundamental improvement in the precision of each individual shell. Some post-war estimates compiled by naval ordnance analysts suggest that the introduction of the proximity fuse effectively multiplied the destructive efficiency of the fleet's existing anti-aircraft batteries several times over, an improvement equivalent, in practical terms, to installing several times as many guns without adding a single additional weapon to any ship's deck, a transformation achieved entirely through the ammunition itself, rather than any change to the guns firing it. The human cost of the alternative, a Pacific war fought without this technology, is impossible to calculate with precision, but naval planners in the war's final year understood the stakes in stark terms. Every kamikaze intercepted before impact is a ship's crew, sometimes numbering in the hundreds, spared the fire, explosions, and structural damage that so often followed a successful suicide strike. Post-war planning documents prepared in anticipation of Operation Downfall, the planned invasion of the Japanese home islands that never ultimately proved necessary, explicitly factor the proximity fuse's demonstrated effectiveness into projected fleet loss estimates. Planners, recognizing that without the dramatic improvement in anti-aircraft kill efficiency the fuse provided, an invasion fleet operating within range of Japan's remaining kamikaze aircraft and coastal defenses would likely have suffered losses considerably exceeding even the brutal toll already inflicted at Okinawa. Every conventional torpedo bomber destroyed before it can release its weapon is potentially a cruiser or carrier saved from a strike that could remove that vessel, and the thousands of sailors aboard it, from the war entirely. Across the full span of Pacific combat where the proximity fuse saw significant use, from the Marianas in June 1944 through the brutal kamikaze campaigns off the Philippines that autumn, and finally the sustained onslaught at Okinawa in the spring of 1945, naval analysts estimate that the fuse's dramatically improved kill efficiency likely saved thousands of American lives that would otherwise have been lost to successful air attacks. The technology instead turned into misses, near misses, or manageable damage rather than catastrophic hits. The campaign off the Philippines in the autumn of 1944 offers its own grim confirmation of the fuse's value, as Japan first began deploying kamikaze tactics in significant numbers during the fighting around Leyte Gulf that October, and American task forces operating in the region, already equipped with proximity-fused anti-aircraft ammunition as standard issue, find themselves facing an early preview of the far larger suicide campaign that will follow at Okinawa the following spring. gathering critical operational experience in countering the new tactic that will prove essential when the far more sustained Kikusui attacks begin months later. The legacy of the VT fuse extends far beyond the Pacific theater, and far beyond the Second World War itself. Adapted for use in artillery shells fired by ground forces once the risk of enemy capture and reverse engineering diminished later in the war, the technology proves devastatingly effective during the Battle of the Bulge in December 1944, where proximity-fuzzed artillery shells bursting above German infantry formations, rather than only on impact with the ground, inflict catastrophic casualties on troops who had previously relied on foxholes and prone positions for protection from conventional shell fire. Protection the new fuse rendered largely obsolete by detonating shells in the air directly above exposed soldiers. American field artillery units, receiving supplies of the new shells only after the security calculus finally shifted in the war's final year, discover almost immediately that the same technology that had proven so effective against Japanese aircraft in the Pacific translates with devastating efficiency into the ground war in Europe. A single artillery barrage now capable of inflicting casualties across an entire exposed formation, rather than only on soldiers unfortunate enough to be standing in the precise spot where a conventional shell happened to land. General George Patton reportedly described the new shells as one of the most valuable developments in the entire history of artillery, a weapon that transformed how ground forces could be engaged even when dug in and sheltered from direct fire. In the decades since 1945, the fundamental principle behind the proximity fuse, using a target's own physical presence to trigger detonation at the moment of maximum lethality, rather than relying on a predetermined timer or direct impact, has become a foundational technology across modern military ordnance, informing the design of everything from surface-to-air missiles to modern artillery shells to the sensors used in contemporary precision-guided munitions. Later generations of proximity-fuzzed weapons dispense with the simple radio reflection design of the original wartime device entirely, incorporating infrared sensors, laser rangefinders, and increasingly sophisticated computer processing to determine the optimal moment of detonation with a precision Tuve's original team. Working with vacuum tubes and hand-soldered components in the early 1940s, could scarcely have imagined, yet the conceptual foundation these later systems build upon traces directly back to the shells first fired in anger off Guadalcanal in January 1943. Historians of military technology consistently rank the VT fuse alongside radar, the jet engine, and the atomic bomb among the small handful of technical innovations that most decisively shaped the outcome of the Second World War. Even though, unlike the atomic bomb, its story has never captured the same degree of public fascination or historical attention, in part because its very effectiveness depended for so long on almost nobody outside a small circle of cleared officers and scientists knowing it existed at all. What makes the story of the proximity fuse so quietly remarkable is not simply the ingenuity of the engineering, cramming a working radio transceiver into an artillery shell that must survive being fired from a naval gun was, by any measure, one of the era's most difficult technical achievements, but the discipline with which the United States Navy managed the secret itself, understanding that a weapon's value could evaporate the instant an enemy learned enough to counter it. Japanese naval intelligence, throughout 1943 and much of 1944, remains genuinely puzzled by the sudden, inexplicable improvement in American anti-aircraft accuracy, some Japanese assessments attributing the change to improved radar-directed fire control alone, never fully grasping that the shells themselves, not merely the systems aiming them, had been fundamentally transformed. That confusion, sustained for nearly 2 years through a combination of rigorous American secrecy and the simple fact that most proximity-fuzzed shells detonate in mid-air rather than surviving intact to be recovered and examined, represents its own quiet triumph of wartime security, an achievement that receives none of the public recognition given to the codebreakers or the physicists of the Manhattan Project, but proves, in its own understated way, just as consequential to the war's ultimate outcome. For nearly 2 years, Nimitz's staff watched a device quietly reshape the odds of survival for tens of thousands of American sailors, and said almost nothing about it, even as Japanese commanders searched in vain for an explanation for anti-aircraft fire that had somehow become impossibly, inexplicably precise. That silence, maintained across some of the most consequential naval engagements of the entire Pacific War, stands as its own remarkable feat of institutional discipline. Hundreds, eventually thousands, of officers and sailors handling the ammunition, loading it into guns, and watching its effects firsthand, and yet the fundamental secret it protected, held firm until well after Japan's surrender made the question of enemy countermeasures entirely moot. War is often remembered through its most visible weapons: the battleship, the bomber, the bomb that ends it all. But sometimes, the technology that changes everything is the one small enough to fit inside a single artillery shell, effective enough to alter the outcome of entire battles, and secret enough that the men whose lives it saved may never have known its name.